Well, this is the last of 3 videos on alcohols, ethers, and epoxides and their polar reactions, and it's the 11th in a series of videos on what is typically Organic Chemistry 2 topics in a university setting. So let's look at ethers that are very much like alcohols, and we're going to draw out that similarity, ethers and alcohols, and there are some differences. One of the big ones you want to note here is we said hydrogen bonding. We have it with OH and NH containing molecules. Well, an ether doesn't have an OH bond. This is an alkyl group, and on the other side of this oxygen is another alkyl group. And so they tend to have lower boiling points, so they tend to, I guess, boil out of solution if you try to heat them up to have them go through a reaction like alcohols. Maybe they can't do it because they just don't stay in solution. And it's not going to be easily protonated, this oxygen here, because it's not, again, in an OH group. This is, and it's easier to protonate this because it's more hygroscopic, or I guess water-loving. This would be less. So then we're going to move after that comparison of ethers and alcohols and the chemistry that they can do that's like alcohols, but it's a little bit less. We'll look at epoxides, which we have a lot of chemistry we can do with these because they are ring-strained. Let's look at the ethers first and compare those to alcohols. So what we'll find is that ethers can react just like alcohols do with halogen-containing acids to give us substitution products. We've seen that with alcohols and halogen-containing acids, substitution products. We'll see it with our ethers. Now we typically have to use HBr or HI as a reagent for these halogenation reactions. HCl maybe also, but not HF. So very limited types of acids that we can use for ethers. We don't really have a line in here that talks about RORs with non-HX acids. There are a few of those type of reactions, but they're very limited. So we'll look at just primary RORs with HX acids. That's going to give us an SN2 mechanism, where these R groups are primary in that they're only connected, the carbon connected to this oxygen is only connected to one other carbon. So we're talking about the carbon within the R group that's connected to this oxygen as being primary, or if it's secondary or tertiary within the ether, and we're reacting with HX, we'll see an SN1 mechanism. And everything that falls out of this, if SN1, then we have carbocation. So that's not too hard. And now let's go ahead and move into epoxides. Epoxides are different. They're like ethers, ROR, but they have ring strain. Because of this ring strain, we have reactivity in 2 ways. We can always protonate this oxygen. That's harder to do in ethers or epoxides compared to alcohols, but we can protonate it. If we protonate it, in acid conditions, nucleophile in the second step after protonation of this oxygen, the nucleophile goes to the most substituted carbon of these 2 connected to the oxygen. That's where we're going to focus, the most substituted carbon of the 2 connected to the oxygen. If we're in base conditions, the nucleophile, the base, goes to the least substituted carbon of those 2 connected to the oxygen. So an example of this might be as follows. If we were to take a buffer solution, let's use sodium cyanide and HCN. HCN is a weak acid, not a strong acid, and we know sodium bonded to anything other than itself, we have a positive charge on the sodium and a negative charge on this cyano group, a cyanide. And we would have, as conditions, we would put as a note, this is base conditions. You say, well, isn't that an acid? Yes, but it's not a strong acid. And so what we really have here is a buffer solution where we have very little of this dissociating in the presence of a sodium cyanide that's in solution also. So we have a buffer solution. It's not a strong base solution, but it's still a base solution. So what would we do with this base solution of cyanide, sodium cyanide, and hydrogen cyanide? Well, we would start with the negative. That's our nucleophile. We're in base conditions, and it would go to the carbon that has the least substituents around it. So we would go not to this one, but to this one. And if we attack, we're going to have to, just like you did in OChem 1, attack from the other side of what's going to leave. Just like in the bromonium ion, when you had two carbons connected to a bromine that had a positive charge, this is very much like it. You have to come in from the opposite side to the least substituted carbon, having the least alkyl groups off of it, is most accessible, and we would kick that off. So I'm going to draw that. Our two alkyl groups, methyl groups, are still over here, and we have now an oxygen with what charge? If you go from owning these two electrons to, sharing these two electrons in a CO sigma bond to owning these two electrons as a lone pair on the oxygen, then he's going to be, and I'm going to go ahead and draw all three lone pairs. He had two to begin with. He would have three, and he would be negatively charged. Now, we just made a strong base from a weak base. This is why we need the buffer, because this would just come right back, kick this cyanide off. But if we have floating around some weak acid, we can have the proton from hydrogen cyanide picked up, and we do two things. We, one, satisfy the oxygen's reactivity. It's a strong base. But notice, we also regenerate our cyanide, so we can have a continuation of this reaction where we're consuming hydrogen cyanide, but we're starting everything with the cyanide anion that when the process will continue to be regenerated. So it's a feedback loop. This reaction gives us a cyanide in the end, so we can have that come around and continue the reaction. Alright, that's our overview of ethers. Know that they go with just HX acids in reactions to either SN2 or SN1 product. And epoxides, remember these two rules. If we're in acid conditions, after protonation, the nucleophile, whatever it is, will go to the most substituted carbon, which in this example here would have been this carbon here. But we didn't go here with our solution that we had because we don't have an inorganic acid here. This has to be an inorganic acid. This is an organic acid, weak. So we had base conditions, so we knew that the cyanide, the negatively charged species, goes to the carbon with the least substituents. Well, we'll end this video with just a little discussion on the synthesis of epoxides. Let's get into it. Different types of ethers with halogen-containing acids. So we said it's protonated RORs react like protonated alcohols. It's not 100% equivalent, but if we can protonate these, just like the protonated alcohols, we make a good leaving group. So it's harder to protonate, but we have the leaving group we need, an HOR as a leaving group instead of HOH, or water, as a leaving group. So there's some similarities. So in secondary, in general, only strong acids, HX acids, generally react with RORs. So we need a strong acid, usually an HX acid on top of that, to have reactions of RORs. These are non-polar, so it takes a little oomph to get them to be protonated. Some similarities with the alcohols. One, secondary and tertiary ROHs or RORs. With HX, we go to carbocation. SN1, go to carbocation. Make sure you draw the carbocation. ROHs or RORs with HX products typically give, in general, substitution products, whether it be SN1 or SN2. HX with ROHs we know gave substitution products, so do RORs, ethers. The difference is, we said that RORs are harder to protonate. They're harder to protonate. And the, little difference. ROHs, or the alcohol, is a worse leaving group than water. It's a little harder to kick this off, especially in aqueous conditions or whatever. It's harder to kick this off. It's not as good a leaving group as water. Maybe there's some debate on that, but certainly this is true. Non-polar compounds are going to be harder to protonate than a more polar compound. Less polar, more polar. I shouldn't say non-polar. Less polar, non-polar. Less polar, more polar. Easier to protonate something if it's more polar. All right. Okay, one last thing about the differences. RORs can give twice as much product as ROH when reacted with an HX, or two equivalents of HX. Why? Well, you can kind of think of it this way. If we protonate the oxygen, let's just show that here. If we protonate, again, we're going to have a little bit of this, a little less than what we had with alcohols. If we protonate, we really have two carbons that can, in the end, be connected to the bromine. So we're going to have one carbon maybe attacked in one step. We kick off an alcohol, but the alcohol can go on to react to kick off water and have a replacement of the oxygen from this carbon with another bromine. So you tend to get two alkyl halides for every one ether compound. Let's show that on the next slide. So let's take our diisobutyl ether, where this carbon connected to the oxygen is primary, meaning only connected to one carbon. So we make those notes. It's really important to do that because that tells us the direction we're going in. If we have carbons that are connected directly to the oxygen that are both primary, then we can say with the HX, we know we have SN2 reaction. So we're going to walk this out in an SN2 manner, where we would protonate this oxygen, so we can just show that. And I'm not going to show the full mechanism here, but we would say at this point we would have, after protonation with HCl, we would have this plus Cl minus. Now we know it's SN2, so we would propose the following, that this chloride comes in and attacks. It's a weak base. You can't have strong bases with acid conditions, but the weak base can attack this carbon that's primary and kick off isobutyl alcohol. And the isobutyl alcohol that would be generated could go on to react, just like we've seen in the last presentation. Isobutyl alcohol can go on to react to make a second equivalence of this alkyl halide. And since we have SN2 reaction, we do not have any rearrangement of any carbocation. There is no carbocation. So we basically, in the end, just cut this oxygen off, put two H's on it, and the two chlorines, if it's both SN2, put them here, and you're done. Now, if we have any other ROR with HX, then we have SN1, and you have to go a little more into the mechanism because you've got to go to carbocation. And if you have to go to carbocation, you have to worry about carbocation shift. So make sure you tag these carbons. And if we do have any secondaries or tertiaries, they tend to go faster in their reaction with the weak base in the second step than the primaries. So you tend to go with the secondaries over the primaries and the tertiaries over the secondaries in terms of what forms first. Alright, so important, determine the products for any ROR, ROH with HX. We have to use the rubric we saw earlier in the notes, wherein we had that protonated intermediate, whether it be the alcohol, like we have here, or the ether. We can still use these notes that we have faster SN1 reactions with a tertiary carbon here than we have of SN2 reactions if this is primary. SN1 reactions are faster than the SN2 reactions for these alcohols, and it's the same with ethers. Alright, so let's take an ether that is asymmetrical, where our carbon here is primary and our carbon over here is tertiary. So which of these two is going to react faster? This one, because the notes for this one would be it's an SN1 reaction mechanism, and over here we'd have SN2. So make your notes. Tag the carbon bonded to the O. Make sure you tag. Tag, tag, tag. And then, I guess, walk out the reactions. And I'm just going to repeat this one here. Tertiary first, secondary, these carbons we're talking about, and then primary. So walk it out. And of course the first thing we do to walk out this reaction, we say strong acid, we tag that primary, we tag this tertiary. We have to walk it out this one first. Strong acids, we know we always, if it's a strong acid, you always protonate. So we're going to have to take the oxygen and have it grab a proton. And in an SN1 manner, we're going to have the bromine attack this carbon. But we have to be careful. We have to consider possible rearrangement. So it's really important to walk it out. To say, okay, what I would do is break away this bond. So I'm going to show that as an intermediate here before the bromide comes in. I would have my alcohol. I'm going to draw this really small so I can draw this. I would have my carbocation, because this bond is breaking back to the oxygen. This carbon's left with a positive charge. Here it is. And it's tertiary. It was here, it's still going to be here, and it's still going to be here. It's still tertiary. So I don't have any rearrangement that I have to worry about. I can have now the bromide just come in and satisfy that carbon where it sits with positive charge. There's no rearrangement. But watch out for those rearrangements with those carbocations before the bromide comes in. They happen faster. Now we're at this point. We've already, I guess, carried out our protonation. The second and third steps was form the carbocation and attack with bromide that carbocation. Now we're starting all over again in a sense, because we have our first product formed with HBr, but we have an alcohol, and this alcohol can continue to react. Just like we had in the last presentation, we would protonate with the HBr, this oxygen, it would be a good leaving group. It's an SN2 reaction, because this is still primary. It was primary back here. It's still primary it was still primary. It hasn't changed. It's now just a primary alcohol instead of part of an ether. It would still go SN2, and we would still have then a reaction at this carbon to make our alkyl halide. So we get two RXs, just like we said you do when you have an ether. You get two RXs. Watch out for the carbocation shift, though, if it's a SN1 reaction that we had to walk out here. We had to start going SN1 first, faster. Watch out for those carbocation shifts. Okay, moving right along, we're going to just have just 3 more slides here. I said we would talk about just briefly a little regarding synthesis of epoxides. So I'm going to do that here. We're going to then talk about reactions of epoxides. If you remember back to OChem 1, alkyl halides react with strong bases or strong nucleophiles. Primary RXs react in an SN2 manner with strong bases. Primary RX with strong base, we get SN2 reaction, where this oxygen with negative charge attacks the carbon that's partially positive while the leaving group's leaving. So we get our SN2 product and our leaving groups off. Okay, well that's great. You all know that SN1 product, sorry, would be favored. Apologize. SNE2 would be favored if a secondary or tertiary RX is used with strong base. We have an alkoxide. I apologize. E2. If the alkoxide is used and we have a more hindered carbon, a secondary or tertiary carbon, then of course you're going to start seeing E2. But what happens is if we take this sort of reaction of a strong base attacking a carbon connected to a leaving group and putting it all within one molecule, then we tend to have an inside, you might say, SN2 reaction. Inside meaning it's all part of the molecule, but our strong base can come in and attack, inside job so to speak, no one from the outside, a carbon that's partially positive connected to a halogen, it's iodine. So it's an in-house Williamson ether synthesis, which we have here. This is a internal or an intramolecular Williamson ether synthesis. We can force this to go to an epoxide by just adding initially to what's called a vicinal halohydrin. This is called a vicinal halohydrin. Vicinal halohydrin. That means we have adjoining carbons, vicinal, an iodine, a bromine, chlorine, and a hydrin, an OH group. If we take a strong, maybe even a bulky strong base like tert butoxide that will only tear off outside protons, we can tear that proton off, create a strong base that now we can use to mimic Williamson ether synthesis, but we're doing it inside. Because our carbon, we're just in close proximity to it, and we can, though it's strained, make a three-membered ring driven by this fact. We're going from strong base, formed by a strong base attacking that proton. We made a new strong base, but in the end we make a weak base. That's what's driving this reaction that allows us to put a structure together that has ring strain. We have to have something driving that. This is driving it, the formation of a weak base from a strong base. Alright, we have just two more slides that we're going to quickly move through in talking about how epoxides react. Not how we make them, but how we react with those. Now you remember from the very beginning, we said that if it's an acid conditions that we find our epoxide in, this carbon will be attacked by the nucleophile. And if we're in base conditions, weak or strong base, it's the less substituted carbon that we'll attack. So make sure you tag the reaction. Strong or weak base plus the epoxide, tag the reaction. So we'd say, in this case, if we have a epoxide and a strong or weak base, go to less substituted carbon. You want to make sure you give yourself a direction that you're going in before you start drawing product, and it comes from a structural analysis. Now in this case, there's no difference, so attack either side, you're going to the same product. But for this one below, we don't have the symmetry. We have asymmetry. So this carbon's more substituted, this one's less substituted. Now we just need to know if we have acid or base conditions. Well, we certainly don't have acid. Is there any strong acid shown here? I don't think so. And there's some catalytic amount of NaOH, a strong base, a catalytic amount of strong base. So we can just put it over here, in base conditions. So what do? We know whatever is the nucleophile is going to attack here. So you can almost just put the head of the arrow right here. Now the tail, this is getting interesting. They use a catalytic amount of NaOH, and if we have a thiol in the presence of this strong base, just mark it through that all catalytic amounts of NaOH react with the thiol, not all of them because there's smaller numbers of this catalytic amount, like spit to cups. We have a spit amount of the thiolate made from the catalytic amount of NaOH reacting with the excess of the thiol. This is our strongest nucleophile, the most reactive, negative containing or electron rich item or molecule in solution, or ion. So this is our nucleophile. Full negative. We're going to attack this partially positive, and we're going to do it in an SN2 style inversion. We're going to connect that SR. This would immediately be negative, but guess what? We can grab more of that proton and regenerate the thiolate, and we can drive this reaction to keep on going and going. Since this proton will get ripped off, we're going to make new thiolate. This is sort of the same sort of reaction we started discussing at the very beginning with the cyanide and hydrogen cyanide. Little feedback loop. So remember, all base catalyzed nucleophilic substitutions involve that inversion where the Y, the nucleophile, is coming in from the opposite side of this oxygen. Sort of an SN2 style reaction. We even see it, I'm going to just mention there are other types of base conditions. I just give you some: hydride, carbanion, amides, hydroxides, alkoxides, amines, and thiolates. we can take and even consider inversion mechanisms for acid catalyzed epoxide reactions. So strong acid, oh okay, strong acid with this asymmetrical epoxide. We know the head of the arrow is going to be coming to this carbon. Strong acid conditions, inorganic acids, I would protonate this oxygen. So I guess I'm going to go ahead and just draw that in here. That would be my first step. And so, well, what do I have left to attack as a nucleophile? Well, you have the conjugate of H2SO4, the conjugate base, but that's a weak nucleophile. And to keep this from getting in the way, we just need a catalytic amount of it. We're just going to have a spit amount of this so we have an excess of the methanol. And the methanol in excess, not because it's a great nucleophile, but just because it's an excess catalytic amount of this to, I guess, equivalent amounts or more of this, we can attack still in a sort of S2 manner. This is interesting. Even though that's protonated and this becomes very labile, very weak, this kind of opens up the face of this carbon on the bottom, opens up, these kind of flay out, because this bond gets really weak as this gets protonated. We're still, though, going to come from the opposite side of this oxygen. That's something unique to this reaction where we're going to the more substituted carbon, but we're still coming in an SN2-like manner. It's the same thing you saw again with the bromonium ion, where you still attack from the opposite side. You still attack that carbon, and you attack, even within the, I guess, bromonium ion, you attack the more substituted carbon, not the less substituted carbon. So that's just similar to what you saw in OChem 1. So we attack the more substituted carbon, fluorines and the methyl groups are bent up. We go from an inversion of the chiral center of R to S, and that H here, I didn't draw it in because that's going to be the catalytic proton that's given back to solution that allows this reaction to run again. So we can say our nucleophile attacks and we lose and regenerate the catalytic proton. So that's our final product. One last one, we can use HBr as our acid. We can say this is not going to work as a nucleophile because we can't lose an acidic proton. So this is just going to be the solvent. If you don't have a proton attached to this oxygen, you can't do what we just did of regenerating the acidic proton. So this is not going to be a reagent. Ether's not going to be a reagent. We can't lose a proton from this oxygen like we did from this oxygen. So HBr, we're still going to protonate, but the bromide is going to come in and attach to that carbon from the opposite side. So it would still go from, I guess, R to S or whatever. Alright, so remember we still have this weak base coming in a sort of SN2 manner, opposite side of this protonated oxygen, and replacing this oxygen. So it's coming in from the opposite side. It's a weakened bond, but we still see inversion of configuration for these acid catalyzed ring opening reactions. Well, that's it. Long video. Bye-bye.